La dernière intervention est celle de Maureen qui vient de l'université de Exeter et qui travaille dans le ESRC Center for Genomics in Society. Nous avons vu beaucoup de visages différents de la biologie synthétique et Maureen va nous proposer une typologie différente de celles qui ont été proposées auparavant, car elle repose sur des critères épistémologiques. Et vous allez voir qu'on a une vision assez différente du domaine que nous venons d'explorer. Maureen, it's your turn.
So, I want to talk about epistemological distinctions in synthetic biology. And by epistemological, what I mean is about how we know and what we know. And of course, that brings in some assumptions, of course, about the nature of the phenomena that we know. But I'm not going to focus so much on the ontology or the metaphysics, but just about this whole process of knowing. And I want to look at it in 4 different levels, all of which have come up today in very interesting ways. And the first one, of course, is synthetic biology as a distinctive whole in itself and what's epistemologically special about it. And then I want to use what Bernadette called my typology, where I look at the different streams of practice and their epistemological distinctions there. And then the third one is looking at synthetic biology in relation to other disciplines, trying to understand what is it that epistemologically distinguishes synthetic biology from other practices in biology and perhaps even disciplines broader than that. And the final thing I want to talk about is what Drew just brought up several times, this whole notion of what synthetic biology is in relation to scientific practice and knowledge making in general. So there's 4 sorts of levels. It's going to be a bit of a fuzzy talk, but I think you'll get the point at the end. So synthetic biology's distinctions as a whole. Now, engineering lies at the core of this, of how synthetic biology is distinguished from other biological disciplines. And what you have is perhaps a quite useful statement here from Jay Kiesling, talking about how you've got overwhelming details in biology, in the natural world, and that these need to be organized and recast via design rules in order to, 1, hide information, so that 2, you can manage complexity. And I think that's as good a description of engineering as we could have. And in this way, engineering then becomes a shaper of all the research practices in synthetic biology, and more broadly, in fact, in that it's not only a shaper of techniques, it's also a shaper of what kinds of data are gathered and how that data is gathered, and the types of research questions that are asked. And very often, engineering practices are characterized by the 3 R's, rationality, then robustness, and reliability of the things that are actually constructed. What I want to look at is perhaps another way of characterizing engineering practice. So the first one we'll look at is analogizing, then synthesizing, mechanicizing, and kludging. So in general, when people start to talk about engineering in biology, you'll start with the analogies of practice. So you'll see engineering as being formulated as having distinctive modes of activity, distinctive work processes. So you start with a blueprint, you gather components, and then you compose whatever it is that you want to construct. And your goal is your product, which is an engineering construction. Traditionally, biology is thought of as starting from the biological phenomenon or phenomena and moving upwards. And generally, it involves some kind of disassembly to understand the parts. So often this is called an analytic approach. And then some sort of modeling might be done in order to get a better handle or to develop an explanation. And the goal is understanding nature. What synthetic biology is saying is, look, you can start at the goal or at the end, at the blueprint side, especially now you've got parts lists such as those provided by genomics, then you can perhaps model out of that, and you can put your molecules back together and end up with a constructed biological phenomenon. But the analogies are not just made, of course, in practice. Very often, as any time you hear people talking about biological engineering, the analogies will be made between the components and levels, the constituents of that bioengineering process. So, for example, you have analogies drawn between modules in electronic engineering and, let's say, pathways or other functional entities in biology. Here's a very straightforward way of looking at it. You've got individual components in electronic engineering, and you've got individual components here in biology. They're put together to make modules which have particular functions. In the case of biology, you might get something like an oscillator. And then in electronic engineering, you end up with complex systems such as a computer, and it's not quite clear whether bioengineering and synthetic biology in particular can go that far. So naturally, with any drawing of analogies, what you get are disanalogies offered in return. And people will often say, but evolution isn't designed, and all natural systems are, biological systems are evolved systems. The connections between parts or modules aren't known. The complexity, therefore, is not maskable. And because of that, the abstraction that is so central to engineering practice is limited. And you get this particularly in relation to the notion of modules, where in most engineering practice, modules will be seen as separable, standardizable, interchangeable, and very stable or predictable parts. And while theoretically there's a lot of resistance to that idea in biology, you also have some experimental resistance, where you have people like Mark Iserlin saying that yes, you can think or try and work with modules, but in some cases this can be misleading, as the behavior of the module is affected to a large extent to the wider network in which the module is embedded. So that's an experimental conclusion. But just as there's disanalogies, there's also a lot of anti-disanalogizing, just to make an ugly word there. And so if you have people saying the cell's too complex for engineering, then the response is quite straightforward. I've taken these from Yuri Lizebnik's paper about whether biologists can make radios or do anything with radios. And what he says is, well, biology can't handle simple systems in the way that an engineer would. They can't predict, they can't control the behavior of those simple systems, so they're not necessarily going to be any better at handling complex systems. And that engineers have got toolboxes, as Drew was pointing out, for coping with complex systems. Lizebnik, he is particularly interested in formal languages and computational power. We'll see how synthetic biology goes beyond that in just a minute. The other disanalogy is a more ontological one, that cells are fundamentally different from the sorts of objects studied by engineers. What people like Lizebnik would say is this is just blatant vitalism, and that there aren't in fact any particularly good a priori reasons to say that cells can't be understood in that way. Then there's also an assumption that goes into that there are deep similarities between living systems and design systems, and that I think is something we can put out there as a very general hypothesis. The third disanalogy is that we know too little about cells to analyse them in the way that engineers might analyse them. What Lizebnik says is we know enough to put together models and find out at least what's missing in our explanations of biological phenomena. But what synthetic biology does is say, yep, that's an okay response to the disanalogy, but we've got to do more. And this is the next aspect of practice that I think is central to the engineering that goes on in synthetic biology, and it's synthesizing. So not just modeling, but actually trying to put things together in a way that will ultimately lead to working and constructed phenomena. So synthesizing is often contrasted, as we've heard a couple of times, to an analytic approach where things are broken down and individualized. That's often linked or correlated with discovery-oriented research. And synthesis plays on these two meanings of synthesis, at least in English, where one side of it's fabrication and construction, making things, the other side is this integration, putting things back together. That's often linked, but isn't necessarily linked to design-oriented approaches. Now, I think in practice, synthetic biology is at least as analytic as it is synthetic. But then there's this special epistemological claim that's made about making as the real source of knowledge. And we heard quite a bit of that from Drew in his wonderful talk that we've just heard. What I'm going to do is leave that aspect right to the end and come back to it as something to talk about as a concluding point. Now, the other aspect of engineering practice in biology, in synthetic biology, is not just to synthesize, put things together, but to mechanicize. So by this I mean putting things together in a rational way and making them work. And I think we can consider this as an art of combining reconstructed parts, using, for example, circuit analogies into obviously functioning devices. Not subtly functioning or invisibly functioning devices at the moment because of I think, the new status that things like synthetic biology have. These have to be very obviously functioning. But why am I calling it an art? So I don't mean this in any kind of pejorative way. I mean it in a sense that synthetic biology and any kind of engineering is a highly creative process. There are two reasons for this. One is that synthetic biology particularly, but I presume other kinds of engineering, it's not about copying, it's about recreating. So it's not copying nature molecule by molecule. And here's the example of the repressor later, the proof of principle, the kind of paradigm case of synthetic biology's success by Michael Elowitz and his collaborators. And what you have is something that's much simpler and, unfortunately, quite considerably less reliable than the natural clock circuits that you might find in unicellular organisms or other cellular configurations. But it's proof of principle for a synthetic approach. My point here is it's about recreating. Second point about why we might consider synthetic biology a creative, artistic approach is because it's got to cope with heterogeneity. So you've got a fluctuation of processes within cells, and even genetically identical cells will have considerable variation in things like gene expression, for example. These are various examples of them here. Then you've got variation in general to deal with in biology, and even variation of standards, even in synthetic biology itself. And as Ken Olsen, the founder of Digital Equipment Corp, said in the 1970s, that the great thing about standards is there's so many of them to choose from. And I think that's possibly one of the problems that synthetic biology will have to confront eventually. Then the fourth aspect of practice that goes on in synthetic biology and engineering and biology in general is this idea of kludging. Now, kludging is a deliberately ugly word meant to give some sense of how a kludge is something that is used to work around a problem. Now, this clumsy, lame, ugly, dumb, but good enough acronym is in fact not a genuine acronym. It was created after the word kludge. Some people say kludge. So these are just various engineering examples of kludges. You can see them. This is an air resistance potentiometer here. Here you've got a capacitator on a circuit board trying to get rid of some of the noise in the electronic circuitry there. The other thing is some sort of robot that's it's got some wiring put in a Tupperware container. Now, I want to get across this notion of kludging as a highly creative and effective process, and that it's linked to this debugging notion, where if you've got any kind of circuitry, any kind of engineering practice, you've necessarily got debugging. And we had some of that come up before in the previous talk. And certainly for software development, debugging accounts for a great deal of the activity that has to be carried out by software engineers. And I don't imagine it will be any different for synthetic biology wherever it goes in the future. Here's a fictional example of a biological kludge. I've got a better one coming up soon. This is just a silly thing saying, kludging is about making things work. They're not about elegance, they're not about beauty. All right? They're not even necessarily about efficiency. If they make things work, it's good enough. And that's, I think, it's a standard engineering attempt to deal with failures of design. Now, synthetic biology, I think, is also about kludging necessarily, and that you have, in fact, many of the emerging applications that have come out of synthetic biology so far, many of the success stories actually being kludges. If you think about the repressor, for example, which is the paradigm case I mentioned before, the simplified clock circuit. Now, when that started off, in fact, what happened was the genes were put the wrong way around. The circuit didn't work. So what did Michael Elowitz and his collaborators do? They then rearranged the genes, not sure whether it would work or not, and in fact, the second time it did work. So kludging is a very kind of pragmatic activity, and I think it's the connection point for biology, engineering, and evolution. So for evolution, we know, if we read people like Stephen Jay Gould et al., that evolution is a history of kludging, of putting things together to make them work, not putting things together to make them beautiful or efficient or elegant, but just to make them work. Biologists also epistemologically kludge all the time in experiments. To make things work is the main thing. It's not to have elegance is a nice thing, but it comes secondarily. And then engineers, I believe, of all types kludge constantly in order to make things work. So I think it's an inescapable aspect of a pragmatic approach to knowledge and construction. But what's curious is that you can see many statements in synthetic biology that you could read as being anti-kludging, that nature and engineering are thought of as being very elegant and efficient. So what I want to do now is just pursue some of this in the distinctive streams of synthetic biology and how these distinctions within synthetic biology itself allow us to understand synthetic biology in a little bit more detail. So this is what Drew was talking about in his talk, something I call DNA-based device construction. It starts with DNA synthesis. It's got these principles of standardization, decoupling, and abstraction. And I think in a sense it's trying to, at least initially, decludge biology, remove the excess, strip things down, streamline it, be able to understand it better by making these simplified systems. And it has many successes or signs of success in doing that. The other aspect is one we've heard quite a bit about today, genome-driven cell engineering. This, I think, encompasses Venter's work, also some other people. And the key practice here is streamlining and modularizing genomes so that you can come up with minimal cells with not too much componentry, fewer genes, less DNA, so that you actually have a more efficient and more comprehensible cell. And genomes here are conceived as decludgeable, relocatable modules, huge modules, but nevertheless, I think, in a very modular way, as the Venter experiments show. And then we have a third stream of synthetic biology that perhaps isn't talked about so much as these other previous two are, and certainly it attracts less public attention, and that's protocell creation, where all kinds of things are done with micelles or lipid self-assembly, trying to put together membranes and information systems and metabolism in order to get very basic cells. And I think many allowances are made for kludging. Again, here, I think the principle that's running it is not efficient, rational design, but in fact, making things work. And you have different aspects of practice in protocell creation, things like protocells and minimal cells, top-down and bottom-up approaches. I'm not going to go into the details about those because I've still got quite a bit to cover. And what a lot of this minimal cell work will lead to is Luca, the last universal common ancestor, which I think through protocell creation could be understood as the original kludge. It's not the most rational thing for nature to have put together, it's not the most beautifully designed thing, but it works, and it gave rise to cellular life as we know it. So, putting back together these three streams, there are some interesting dynamics between them. If you think about cellular context, for example, in relation to genome-driven cell engineering, the type of work Venter's doing, and DNA-based device construction, for one stream of synthetic biology, the DNA-based device construction, cellular context is problematic. It stops things working. Whereas for the genome-driven cell engineering, it's far less of a problem. It's basically ignored. The idea is you put your genome into a cell of some sort that's had the genome removed, the chromosome removed, and it should work. And if many of the transplantations don't work, that's okay as long as one or two do. So you've got a deproblematization of cellular context there. If we look at this epistemological strategy of genetic determinism, we see again some very interesting differences between genome-driven cell engineering and protocell creation. For the genome-driven cell engineering, all that matters really is the genome. The genome is the source of everything. It will run the cell. Whereas for the protocell people, you've got a much more egalitarian attitude to the notion of information and the carrier of information, if it's a genome, that's equal to metabolism, equal to membranes. So there's no special privileging of genomes there. And then finally, we have this other epistemological tension of complexity and emergence and how that's understood and dealt with. And I think for DNA-based device construction, you see that factored out. Whereas for the protocell people, there's more of a tendency to factor it in and just think, well, that's nature for you. We can't do much about it if we want to develop cells. But it's not enough to understand synthetic biology in isolation. It needs to be understood in a disciplinary context. And I think here there's some interesting unclarities, and it's nothing I've been able to work out very clearly, the role of synthetic biology in relation to other disciplines. You can think of it as an approach, as a tool or a set of tools, as a field perhaps, you see it often called a field, as a discipline. Many people think of it as a proto-discipline, and for some people it's in fact an application strategy. So here you have a diversity of relationships. I just wanted to go through a couple of concrete examples where it's not particularly clear what sort of role synthetic biology is playing in relation to other disciplines. SB stands for synthetic biology there. It looks like a disciplinary nexus. It's not clear whether it could be a discipline in and of itself, or perhaps just a toolbox that those other disciplines draw on out of necessity and in order to actually do more with their own research. Here's a new and very large institute in London that's just been created, the Systems and Synthetic Biology Institute. What's interesting here is to see that synthetic and systems biology are invisibly absorbed to all these other disciplines, tools, applications. So I think I'm not going to go further into those disciplinary relationships at the moment, what those might be, but it does seem to me this is a very interesting question to understand how synthetic biology might develop, and in fact how it might reconfigure our notion of what a discipline is, and even how research is carried out institutionally. But if we are going to think about other disciplines or other research activities, as has been made clear a couple of times, systems biology is probably the other approach that we have to think of if we're trying to understand in relation to other activities how synthetic biology fits in the research world. Now, many people see systems and synthetic biology as two sides of the same coin, that they're fundamentally different, but they have complementary outlooks. And the differences are often seen or represented in the systems biology is about formal abstraction, so we're back to the mathematical modelling here, whereas synthetic biology is actually about instantiated mechanisms, things that are made to work in biological systems. And for other people, this actually adds up to mean that systems biology is knowledge-driven and synthetic biology application-driven. And this way of thinking conceives of genomics, for example, as a source of data that enables systems biology, which is where models are produced, and that synthetic biology is about practical achievements. And I think these sorts of division or that kind of historical continuum is a little bit too simplistic, especially when you start to think about synthetic biology in relation to metabolic engineering and how these two are related to each other. So here we have this European Commission report, the NEST report, that I think has been cited in the little historical thing at the beginning of the program. And what this does is make some very interesting distinctions between tinkering, which is metabolic engineering not doing very much, only minor re-engineering, and synthetic biology, which is rational, design-based engineering that's going to do an enormous great deal more. And the curious thing here is, I think that one of the key application successes, this artemisinin precursor that a couple of people have talked about already, in fact is developed through, I think, through what we would call a fairly traditional approach to metabolic engineering. It's not full-blown synthetic biology. It's not about rational redesign of entire systems. In fact, it's metabolic engineering making a particular pathway work, albeit in a different cell, and not particularly knowing why it works in these different cells. And from a metabolic engineer's point of view, of course, synthetic biology isn't something that encompasses metabolic engineering and takes it over. In fact, synthetic biology is just one of the contributors to successful metabolic engineering. The other contributors are protein engineering, computational systems biology, and various bodies of omics data. And this, I think, we can use as a pivot point to get into this idea of knowledge as making. So what we have here from this famous paper of Steve Benners and the SysMol in 2005 is the idea that if you can put together metabolic engineering and synthetic biology where they're not sort of separated out as one being superior to the other, that we can actually use this to understand metabolism, metabolic processes in cells far better, and that synthesis in this account is what drives discovery and learning. That brings me to the final aspect of epistemological practice that I want to look at, and this is the equation of synthetic biology with making being knowledge-making. And very often Richard Feynman, the famous theoretical physicist, is used to justify this stance. Now, Feynman died in 1988. This is his last blackboard. And he had this little thing at the top saying, "What I cannot create, I do not understand." And this has become a kind of rallying cry, I think, for many synthetic biologists. And it's a very interesting one, and it's a curious one too, because of Feynman being a very pure theoretical physicist who didn't do any experiments himself. I doubt he was saying he didn't know anything. And he also has said other interesting things that I think bring this whole epistemological notion into at least question or something more to think about. So Feynman was famously involved in the commission that was set up to inquire into the explosion of the Challenger shuttle in 1986. It exploded 73 seconds after liftoff, and everybody was killed. And it came down to what Feynman's demonstrating here, I think, at the end of one of the Congress hearings. Now, he fell out with the inquiry that looked into the explosion, and he never actually produced a report with them. He produced an appendix that was tacked onto the end. He became very anti this idea of top-down engineering because he thought it led to many failures of process. But what he's doing here, he's got the famous O-rings from the fuel tanks, the hydrogen fuel tanks. He's showing that if you immerse them in ice for some time, they lose their pliability. And then if you warm them up very quickly, what happens is that they actually rupture in various ways, and they lead, this is what led, most people believe now, to the explosion of the fuel tanks and the loss of the Challenger shuttle. And what Feynman says in relation to that, something that is quite different from the previous statement about what I cannot create, I do not understand. So here he's saying you can never be sure that all the bugs are out, and that for some the fix may not have addressed the true cause. So what we have here again is a distinction made in the way that we generally understand it between making things and actually having true knowledge of them. So I think what I'll end with are these epistemological distinctions between this idea of rational ordering of nature versus the untidy making do that much of engineering and biology can consist of. That there's this distinction between pure engineering of rational design and kludging, putting things together to make them work, which I think we can say is at least as important in engineering as rational designers. Then we have also this disciplinary rhetoric, seeing synthetic biology as a discipline, versus this collection of technical achievements and failings, and how we understand that as a discipline, and in fact what discipline means in this post-genomic age of biology. And finally, going back to the Feynman statement, we have this distinction made between causal knowledge and practical construction. So I don't want to resolve those questions, of course I can't, but I do think that the future history of synthetic biology will be fascinating for what it tells us about those sorts of epistemological questions, whether it can work within those tensions, and or whether it needs to and whether it can actually resolve those questions, put them to the side perhaps, and whether synthetic biology needs a special epistemological and disciplinary status in order to deliver its promises, or whether it's going to be able to deliver what it promises just as a kind of adjunct, something that is absorbed invisibly into the rest of biology. So I'll leave it there with those questions. I've got a few acknowledgements, and that's it. Okay.